Hello. These two topics we're going to look at now are going to be very important if you take math and another course going forward, but they're also very important in terms of physical situations, and I'll try to describe one here in a minute. We're talking about average rate of change and the difference quotient, or an instantaneous sort of rate of change of a function. So these are properties of functions. By definition, an average rate of change of a function is how that function changes on the interval AB, and it's really given by the slope. So it's pretty simple to compute. So the average rate of change is just going to be equal to the change of the y value, the function value, over the change of the x value, change of y over change of x. So that's going to be the function at b, the y value at b, minus the function of a, the y value at a, all over the difference in the x value, so b minus a. The Greek letter delta here just means change in that variable. So we're going to try to find an average rate of change for this function. I plotted it here. This is our parabola here. F of x is equal to negative x squared plus 3x minus 6 on the interval from 2 to 4. But you can sort of think of it as how this function, the blue function, would change between 2 and 4. So I've put this line in there just to sort of represent what we're looking for. So if I evaluate the function at 2, I'm going to be at this point of the line. And if I evaluate the function at 4, I'm going to be down here. So the slope, if you sort of think about the olden days when you were driving maybe on K10 and you had a cop that clocked you at one point and then a cop that would clock you at another point, that's like a speed trap. So they would take the difference in those values of your speed divided by the distance, and that would be how fast you were going over that interval. This is sort of the same idea here. It's going to be given by the slope. So one thing we can see when we compute this answer is our average rate of change is going to be negative because the slope of that line is going down. So we're going to be decreasing. So let's go ahead and compute this by using the definition. I want to find f of 4 minus f of 2. That is going to give me the change in the y. So I'm going to just write that here, all over the change in x, and that's going to just be 4 minus 2. So these are two x values here, x1 and x2 on the interval, and I want to find the slope. So what we're going to do is we're going to compute the function at these values. I'm going to have negative the quantity 4 squared plus 3 times 4 minus 6. And then I'm going to subtract off. I'm going to put this in big parentheses so I remember to distribute through if I need to. The function at 2, so negative 2 squared plus 3 times 2 minus 6 all over 4 minus 2. All right, so calculating, I have 4 squared is 16. I have negative 16. Plus 3 times 4 is 12 minus 6. Minus, I have 2 squared is 4, so I have an opposite of 4. 3 times 2 is 6. Minus 6. Again, all over 2. And I'll bring things over here. I'll have negative 16 minus 12, or plus 12 is negative 4 minus 6, that's negative 10. Minus, I have negative 4 plus 6 minus 6, so that's negative 4. All over 2. When I subtract the numerator, I have negative 10 minus a negative 4, so that's negative 10 plus 4, negative 6 over 2. And so our average rate of change, or our slope, will be 3. So again, looking at this graph, the slope of that red line should be 3. And if you sort of look at what I have there to plot them, you can see that I plotted the first graph. And yes, my slope here using that slope-intercept form of a line fact, it was the point slope form, it's going to have the slope of -3. So that's the line that goes through those 2 points in the curve. Okay, now the difference quotient helps us compute the change of the graph at almost 1 point. So now you're driving down K10, and this is what would happen nowadays. So the cop has a radar gun on you, and bam, they get your speed at 1 instant. And if you're going over 75 or whatever, you're busted. So we're going to try to find the rate of change of that function at any point. That's what the difference quotient does. And to do that, we're going to be using this formula. So what we're going to really be doing is, if you look at this graph, we're going to, now I know that this is a little more less intuitive, but we're going to be looking at a point C. So C could be there at 2. Let's just pretend it's at 2. So what we're going to do is we're going to compute the average rate of change between that point C, and if we add on a little value h, maybe a point right over here, so a small value of h. So now we're looking at the slope between these 2 points and the y value. So now we're looking at this little slope here. We're getting closer and closer to that point 2, or C, wherever we want it to be. All right, so you're just one step away from calculus here. But if you do take calculus, then you'll be able to find the exact speed at that point. So when we evaluate this, notice the denominator. When we take C plus H, that little bit minus C, that just boils down to H. So we can just compute this value. So I'm going to do it at any point C, and if we want to at the end, we can plug in 2. So I have f of C plus H minus f of C all over H. So warning, our answer will have H's and C's in them. All right, so I go and I look at my f function. Wherever I see an x, I'm going to plug in a c plus h. So I have negative c plus h squared plus 3c plus h minus 6. Then, just like above, I'm going to subtract off in big brackets f of c. This says take that function, and wherever I see an x, I'm going to plug in c, negative c squared plus 3c minus 6. And then I'm going to divide everything by c plus h minus c, but we said that that was h. All right, next step is I'm going to have to simplify things a little bit. So I'm going to take c plus h times c plus h. We've done this before, but if you have to, go ahead and do c plus h times c plus h. When you do that, you'll get c squared by distributing, ch, another ch, and then h squared. So we're going to have minus c squared plus 2ch plus h squared. I'm going to drag that 3 through. So we'll have plus 3c plus 3h minus 6. Now I'm going to go ahead and distribute that negative through. So negative c squared is c squared minus 3c minus a minus 6 is plus 6. The last thing I need to do before I start canceling things out is I'm going to go ahead and put this negative through in the first term. So I'll have negative c squared minus 2ch minus h squared plus 3c plus 3h minus 6 plus c squared minus 3c plus 6 all over h. What will happen with these difference quotients is always sort of the same thing. A lot of things cancel out. So the c squareds should cancel out. They subtract out there. The 3c's subtract out. Lots of cancellation. The 6's cancel. And so we're really left with a pretty simple expression here. And this happens almost always. So negative 2ch minus h squared plus 3h all over h. The last thing we can sort of do here is see, hey, everything in the numerator has that common factor of h. I can factor that out, and we'll cancel it with the denominator. So if I factor out that h, I get negative 2c minus h now plus 3. And now when I divide by h, these factors cancel. And my answer for the difference quotient is negative 2c minus h plus 3. So what does that mean for our speed trap example? So what that means, if we were looking for the slope exactly at that point 2, then, so this is a little extra. So we can say the rate of change at c is equal to 2, that x value is equal to 2 would be, I'm just going to call it m, negative 2, I'm going to plug in 2 for c, minus h plus 3. So that's going to give me negative 4 minus h plus 3, or negative 4 plus 3 is negative 1 minus h. Finally, in calculus, to get that exact point, remember that h, what that was that was just going to move just slightly past the 2. So if we just move slightly past the 2, we want it exactly at the 2. We're going to let h go to 0. So that's what they would do in calculus. So if we let the h go to 0, we would get the slope, or the rate of change at that point, is equal to negative 1. Now that's past what we're doing here, but we can put that into our calculator now. And if I graph these two again, let's see if this works out, and I'll show you. So now I have a different line, and you can see it's tangent. So it just hits at that 1.2. The slope of this line is going to be negative 1. And so you can verify that by just looking at the graph that I have there that goes to that point, 2, 4, or 2, negative 4, and then has a slope of negative 1, which we computed. What you're responsible for is just this difference quotient, though. All right, very interesting stuff. I hope this has helped.